In this video we're going to look at one of the practicals that has been mentioned on the GCSE Advanced Information for OCR 2022. This is measuring the speed of sound for physics, so separate science. Now there's a few methods they could use and it's hard to predict what might come up, so I'm just going to go over three fairly simple methods in this video. So the first one, hopefully this video will focus in a second, is a very simple method where you clap or you make a sound. The sound travels to the wall, it bounces off the wall, it reflects off the wall or echoes off the wall, and then is detected usually by another person. And if you know the distance and the time, it's really easy to work out the speed. So we know that speed equals distance over time. So it's really simple. We think about the distance that the sound has travelled and the time it takes to go there and back. So in this case, the distance between the wall and the person is 480 meters, but the sound is going there and back. So we've got to times that by 2, and then the time that it takes might be some random time, I don't know, let's just say 0.5 seconds just as an example, so then we can work that out. So that would be that would be 960 divided by 0.5, which would be 1920 meters per second. So this example here, you might already think, oh, that's a really silly example because this is nowhere near the speed of sound. You should know the speed of sound is approximately 340 meters per second. So if you ever get an answer that is roughly, it was not this, or you know, roughly this, it might be 300, it might be 350, it might be 360, you're clearly wrong. So this time is clearly wrong, but the method is absolutely fine. Okay, let's look at another method. This is perhaps even simpler, but sometimes it catches people out. So here you have a speaker, and here you have a microphone. A microphone is just a sound detector. So here you emit a sound wave, it travels from the speaker to the microphone, and it's detected. And again, here you use speed equals distance over time. So here it's a bit more simple because the distance is traveling from here to here and the time is from here to here, so you don't need to multiply anything by 2 or divide anything by 2. So what they often pair this with is a trace that the microphone is actually giving you. So we've got not the microphone, that the data logger here is giving us. So we know when the sound is emitted from the speaker and we know when it's detected from the microphone. So the time between the two is whatever this time difference here is. So it would be roughly 0.28 seconds here. So really simple method. Obviously that distance, whatever that is, might be a meter, 10 meters, just distance over time. Now sometimes this time might be in milliseconds. So if it was in milliseconds, that is 10 to the minus 3 seconds. So you know, 1,000 milliseconds would be 1,000 times 10 to the minus 3 seconds. So that would be 1 second, or 500 milliseconds would be 0.5 seconds and so on. So sometimes that's how they catch you out. Occasionally they might give you this kind of trace, but for an echo. So you might have this trace where it's like this, and then it kind of keeps repeating. So we've got an echo, we've got an echo, we've got another echo, and so on. And sometimes they say, like, you know, the time between 3 echoes was some time, so you'd have to go, right, that's the time for the first one, second one, third one, that's the time we need, and recognize that if it's the third echo, it's actually gone 6 times whatever that distance is. So they can combine these two methods sometimes to make it more complicated. This method here is basically exactly the same as this. You have some sound, but there's a subtle difference. The sound is emitted, it is detected first here, and then it's detected again second here. And the time difference between them is given and the distance between them is given. So again, speed is distance over time. So it's a very subtle difference. It shouldn't really catch anyone out. It shouldn't affect the maths or the questions, but they can present it in different ways. So it's possible they come up with another arrangement that's not here, but here are at least 3 or 4 common ways of doing it. So in order to practice, I've got a few questions here for you to do. They are quite simple, but if you pause the video now and try all of these questions. So part I, the student did not pay attention when recording time 3. Calculate the mean time taken for the sound of the clap to return using suitable values from the table. So this is a really common question, but often they miss this out. Now what they expect you to do is realise, right, that's sensible, this is sensible, this is clearly an anomaly, so you need to ignore that. And I have seen questions where they leave this out and you're expected to recognise there's an obvious anomaly. Now, how do you know if it is an anomaly or not? Well, one reason to suspect it is if it's just really far away from the other two. Really, that's the main reason. You know, if this value here was 0.14 seconds, this was 0.32, and that was 0.54, you might say actually there is naturally quite a big range, I will use all 3. But because these two are really close together and this one is really far away, we can probably be confident we ignore that. So the mean time is clearly this plus this divided by 2, which is 0.30 seconds. Calculate the speed of sound for the clap. So we know that speed is distance over time. So what's the distance? It's going to be 100 meters, so 2 times 50 meters, because the sound goes there and back, divided by the time taken. We use this mean time here, 0.30 seconds. So that's 100 divided by 0.3, which is 333 meters per second. And that is fairly close to 340, so we could be fairly confident that is correct. If you'd forgotten to times by 2, you'd get an answer of half of this, and you'd hopefully realise you're wrong. Now, there's something missing here. I suspect that was 2 significant figures, so always check what this is. You know, obviously, my mistake means you couldn't have answered that, so probably I would have written this. Okay, very common question. Describe 2 ways to improve and develop their method. So, repeat more times, and that's basically to compensate or to deal with the fact that one of our values was wrong for anomalies. Now this actually does say describe, so you don't need this bit, but I like to explain why. The other common improvement is use a longer distance to the wall. So instead of 50 meters, maybe 100 or 200 meters. The reason for that is the biggest source of error here is going to be the reaction time, starting and stopping the stopwatch. So if the time it takes is only 0.3 of a second, your reaction time is probably 0.1, 0.2, 0.3 of a second. So your reaction time is a significant fraction of this. But if you use a distance that is much greater, that's maybe, I don't know, 500 meters, so 10 times as great, well, your reaction time, you know, if the time is 2.8 seconds and your reaction time is only 0.2 seconds, then actually that is a tiny fraction of that, so your error is less. So that's why this is a really common improvement. Okay, question 2. Describe what measurements he needs to measure this speed. So what speed are we talking about? So we've got a ball being hit by a bat. Here's the sound a short time after. It's because the speed of light is greater than the speed of sound. So what measurements does he need? So it's a 2-mark question, so we need to write 2 things, and you've probably got the theme here. We need to know the distance from the person to the student, or sorry, that's a bit vague, isn't it? Distance from the ball to the student measuring. And we need to know the time delay, or the time taken for the sound to get there. So it's a fairly common theme in at least these questions I've chosen. Speed is distance over time. What equation is used to calculate speed? Speed equals distance divided by time. However, on the formula sheet, I think it is actually given like this. So in general, I would encourage you to just literally copy things off the formula sheet, just to avoid making any mistakes. You know, I'm sure you all know how to rearrange, but we never want to make a silly mistake, especially if it was a bit more complicated, like, you know, kinetic energy. One way you could get valid results for this experiment, the answers are exactly the same as here. Really, you want to repeat many times, say to compensate for any anomalies or your reaction time, and use long distances again to reduce that that percentage uncertainty, that percentage error from your reaction time. And then finally, question 3. This is really easy, but just a common kind of question. Which has the largest range of values? So you've purely got to go down this list here, and you've got to find the one that has the biggest range, which hopefully I've done it correct, and that is C.